Hello, my name is Shahriari, and this is a lecture in a series of lectures on abstract algebra. In particular, this is a third on lectures on ring theory, and the purpose of this lecture is just to give you some examples of rings and fields. When we study an algebraic object, we always like to know that there's lots of examples so that we're not studying in vain, that the theorems we prove, the things that we say can be applied to a wide range of objects. And rings are no exception to that. And so let's get started. So let me just remind you what rings are. So a ring is a set, an abstract set. We are not identifying what the elements of the set are. We're just saying we have got one set and we have two operations that we're naming, we're calling addition and multiplication. And the set together with the addition should be an abelian group. So that means that it's closed, it has it's associative, it has a additive identity, which is 0, and it also has additive inverses. So every element there's a minus a, and it's abelian, which means that it's commutative. A plus b equals b plus a. With multiplication, we only expect there to be closure and associativity. And in addition, we have distributive laws connecting the two operations. So that's what a ring is. Now, if ring happens to have a multiplicative identity, what we call a 1, then we call that a ring with 1 or ring with identity. If it happens to be that multiplication is commutative, then it's called a commutative ring. If it has an identity and it's commutative, then it's a commutative ring with identity. An integral domain is a special kind of a commutative ring with identity, one that had at least two elements. The only ring with one element is the ring just 0. Some authors would like to call that integral domain also. I don't. And when the ring has more than one element, the 0 and the 1, there will be a 0 and a 1 if it's a ring with identity, and those will not be the same. But the most important part is that R does not have any 0 divisors. Those are two non-zero elements that when multiplied will give you 0. So there's no such thing. There's no element that has some other non-zero element that you multiply by and get 0. Even a better thing than an integral domain is a field. When you have R minus 0, when you throw away 0 with multiplication, you get an abelian group as well. So in a field, you can not only add, subtract, and multiply like you can do in a ring, but you can also divide, and both addition and multiplication are commutative. Okay, so let's get started with our examples. Our first example is just the ordinary integers with ordinary addition and multiplication. 3 plus 5 is 8, 2 minus 3 is minus 1. This is our prototype of an integral domain. In fact, it's the integral domain that all other integral domains aspire to be like. They like to be like the integers. If you ask any integral domain, that's what they like to be. Some make it that far, some don't. And the reason is that the integers have lots of interesting properties in addition to being an integral domain. For example, we have the division algorithm. When you divide one integer by another, you might not be able to fully divide because integers are not a field, but you can divide and get a quotient and a remainder, with the remainder being small compared to the thing you divided by. We also have the fundamental theorem of arithmetic. Every integer is uniquely written as a product of prime numbers. Well, not quite uniquely. You can switch around the places of the primes or multiply by minuses. But other than that, those sort of trivial things, every integer has a unique factorization into primes. And because of that, we have divisibility, we have primes, we do number theory with integers. And as I said, other integral domains, we might categorize them based on how close they are to this model, to the integers. And that this will come in future lectures where we do that, when we find those kinds of categories. As a part of integers, we can look at the multiples of the integers. So multiples of 5, for example, multiples of 7. Those are also a commutative ring, but they're a commutative ring without identity. So if you look at multiples of 5, that would be 0 plus or minus 5 plus or minus 10 plus or minus 15 and so forth. If you add 2 of those, you will still have a multiple of 5. If you multiply 2 of them, you get a multiple of 5, but you don't have identity. You don't have anything that multiplied by other things doesn't change them. This is an example of a subring, which will be the subject of the next lecture. These are subrings of the integers. Okay, so our first set of examples other than the integers are what's called quadratic integer rings. So you start with an integer d, could be positive, could be the negative. You just don't want it to be divisible by the square of a prime. That might sound like a strange thing, but the reason for that is that you don't want, so when you take square root of it, you don't want anything to come out of the radical. So for example, you don't want 12 because square root of 12 is really 2 square root of 3. And that's because 12 is divisible by 4. So just take some, you can take a prime, for example, but you don't have to take a prime. You can take 6 because it's 2 times 3, but don't take 4 times 3, which is 12. Okay, after you pick an integer like that, then you look at the set of numbers that are of the form a plus b times square root of d. What are a and b? A and b are integers. Just pick your whatever integers you like and make that linear combination, a plus b square root of d. This set includes the integers because you could pick b to be 0. So the integers are a part of z joined square root of d. You can think of this as extending the integers to a bigger set. And in fact, and this is an integral domain. When you multiply two of these, you will never get a 0 when neither one of them is 0. It is a ring because when you add two of these, you get something like them. You can combine terms and you get something like them. And the same when you multiply two things like that, and they follow all the rules. Most of the rules they follow because they're already a part of the complex numbers or real numbers, and those follow the rules. Okay, now this is a ring that in solving Diophantine equations is very useful, as you might have seen in the first lecture in this series of lectures on rings, where we talked about the relationship between this ring and Diophantine equations. As examples, for example, you could take d to be minus 1. Then the square root of d will be just I, and you're looking at a plus bi, where a and b are integers. That has a special name. That particular ring is called the ring of Gaussian integers. Another example would be if you pick d to be 2, and you would get things of the form a plus b root 2. By the way, as an aside, if d happens to be 1 mod 4, that means that d is a number that when you divide by 4, you get remainder 1. So for example, like 5, then you can have another quadratic integer ring, which is of the form a plus b times 1 plus square root of t divided by 2, where a and b are integers. Now, this looks like a little bit odd, but and it's not actually clear that this is a ring, because it's not clear that if you multiply two things like this, you will get another thing like it, but you will, and you can try it. And in fact, it won't work if d is not 1 mod 4, but this is actually ends up being an integral domain that's important in number theory. Okay, in this, while we're here and we're talking about quadratic integer rings, we want to talk about one map called the norm map that these guys have. Other rings don't have something quite like this, although there are generalizations to all kinds of other situations. But if for this particular quadratic integer rings, we have a norm map that ends up being really important. So again, d is an integer, positive or negative, that's not divisible by square root of a prime. And again, z joined square root of d is a plus b square root of d, such that a and b are in z. I say z joined square root of d because the way I'm thinking of this is that I started with the integers, and then I have this square root of d guy, and I want a ring that contains the integers and square root of d, and that's the sort of the smallest ring that will do that. This construction of the quadratic integer rings is a particular case of a more general construction that we will see when we talk about polynomial rings in detail later. I mean, I will give the example of polynomial rings later in this lecture, but later we will discuss them in much more detail and in much more depth. So the map that we're interested in, this norm map, is a map that takes elements of the quadratic integer ring and gives you an actual integer. And it's defined by n of a plus b square root of d is going to be a squared minus db squared. Okay, so that's a function. You do get, you plug one of these guys in. The domain is z joined square root of d, and the target set is the integers. This is called the norm map. And one thing to note about it is that where did that a squared minus db squared come from? One way to think about it is that it's the product of a plus b square root of t times what's called its conjugate, a minus b square root of t. An important property of the norm map, the thing that puts this map on the map, is the reason we are interested in it, is that if you take two elements of z joint square root of d, I said a plus, I don't know for what reason I put a plus b square root of d, I should have said just square root of d. This is going to be the same thing, but joint square root of d. If alpha beta are two elements of that, then the norm of alpha beta is norm of alpha times norm of beta. So we have this multiplicative property of the norm that becomes super useful. And in fact, if you watch the first video, we already used that to show how we use quadratic integer rings in norms. Again, this is a little typo here. This should be z joint square root of d, not a plus b square root of d. Now, this map N is not a ring homomorphism. Ring homomorphism is something that we'll talk about in 2 lectures down. But in general, N of alpha plus beta is not N of alpha plus N of beta. Okay, on to our next example, integers mod N. So you pick a positive integer, and z mod nz is going to be, you can think of it as the integer 0, 1, 2 through n minus 1. And addition and multiplication is going to be mod n. N should be actually greater than 1, so 2 or larger. So this is a commutative ring with identity, and it's called the ring of integers mod n. The group of units, every ring, when you look at the elements in it that have multiplicative inverse, that forms a group, and that's called the group of units. We saw that in the previous lecture. In this case, that's all the elements of z mod nz that have the greatest common divisor with n is 1, that are relatively prime to n. Those elements form a group. We have seen that in the group theory lectures way back, and that's the group of units. Now, if p is a prime, then that group of units will be everything other than 0, and that makes z mod pz a field. But if p is not a prime, if n is composite, if z mod nz is not even an integral domain, so there's nothing in between. So you either have a field where n is a prime, or you're talking about a composite thing, and then you have 0 divisors. And the reason for that is pretty clear. If n is composite, then you can factor it, and then those two things multiplied will give you 0 in z mod nz. So in z mod 6z, for example, 2 times 3 is 0. So 2 and 3 are both 0 divisors. By the way, in the case where n is a prime, and then the field z mod pz will be denoted by fp, field with p elements. F for field, p for the fact that it has p elements. And we call that the field with p elements. The reason we call it the field with p elements is because it's actually unique. There's only one field. All fields with p elements are isomorphic to each other. That needs proof, and we're not ready to prove that. We prove that much later in the course of these lectures. Okay, now we move on to polynomial rings, which are another source of example for rings. So you start with any commutative ring with identity, any one you like, maybe the real numbers, maybe complex numbers, maybe one of those quadratic integer rings, any commutative ring with identity. And then Rx is going to be the set of polynomials in the variable x with coefficients in R. So you pick polynomials, but your coefficients come from a commutative ring with identity. And so an element of this Rx is going to be a polynomial. And that means that it's something of the form a0 plus a1x plus a2x plus ... plus an xn, where n is some integer, and a0 through an are elements of the ring. Those are the coefficients, and those are the elements of R. How do we add and multiply? Well, we just do the usual addition and multiplication of polynomials. So yeah, and that will make this a commutative ring with identity. Identity is going to be the polynomial 1. When you multiply that by other things, nothing happens. And this is called the ring of polynomials over R. The over R means that that's where the coefficients are coming from. they're coming from R. Now, the R in this Rx can be any commutative ring with identity. And so I'm going to give you two examples of that. So for example, you can take R to be Z mod 3Z, the thing that I called F3, the field with three elements. And so then what that would mean is that we have the ring of polynomials with coefficients from F3. F3 has three elements, 0, 1, and 2. So for example, if I ask you what are the polynomials degree 1 in F3x, then they will be only these guys, x, 2x, x plus 1, 2x plus 1, x plus 2, and 2x plus 2. We don't have anything else because the coefficients are elements of F3. And we do arithmetic in F3. So for example, when we add x plus 2 plus 2x plus 2, we use the usual addition of polynomials. So x plus 2x is 3x, but 3, that coefficient, is 0 in F3. So that goes away, and 2 plus 2 is the same as 1. So x plus 2 plus 2x plus 2 is 1. And if I multiply x plus 2 and 2x plus 2, well, then I get 2x squared plus 2x plus 2x plus 4x, but 4x is the same as x, and 2 times 2, 4 is the same as 1. So I get that, and then x plus 2x is 3x, and that's 0, because again, the coefficients are in F3. And so I get 2x squared plus 1. So that's an example of how you might do arithmetic, addition, and multiplication in the ring F3x. But as I said, this R could be anything. But if R is a commutative ring with identity, then the polynomial ring itself is a commutative ring with identity. So we can use it, S, Rx, as the coefficients for a polynomial ring. So what might do is we can construct SY. Now, what's S here? S itself is the ring of polynomials with coefficients in R, the polynomials in X with coefficients in R. So this XY, S of SY is really Rx Y. And the way we write that usually is Rxy, because if you have polynomials in Y and the coefficients are polynomials in X, if you multiply that out, what you have is polynomials in two variables, X and Y. And so this is also commutative with identity consisting of polynomials in Y whose coefficients are polynomials in X. And after simplifying that, this is polynomials in two variables, X and Y, and with coefficients in R. And we can continue this, adding new variables, and we can write R bracket x1 through xk is a ring of polynomials in k variables, again with coefficients in R. Now, usually in the study of polynomials, and we will see this in detail much later, the polynomial ring reflects some of the properties of the ring of coefficients. There's a close connection between the ring of coefficients, what kind of properties it has, and the polynomial ring. So for example, if R is a commutative ring with identity, if and only if the polynomial ring is a commutative ring with identity. And the polynomial ring is an integral domain, if and only if the ring is an integral domain. The variables aren't going to cause you a zero divisor, but if R already has zero divisors, well, the polynomial ring will also have zero divisors. Okay, moving on. Now we want to talk about rings that we can make out of matrices. So again, we start with a commutative ring with identity, and then we look at n by n matrices whose entries are from that commutative ring. We add and multiply those elements, those matrices, using the usual matrix addition and multiplication. This is not commutative anymore. So this is not a commutative ring anymore. It's a ring with identity, but not a commutative ring because matrix multiplication is not commutative. What's the identity? Is the identity matrix. The identity matrix, when you multiply it by other matrices, you get that matrix back. Now, this is not necessarily commutative. It could be commutative if, for example, n was 1. Then if you looked at 1 by 1 matrices, then it would be commutative. Let's look at an example. If we look at 2 by 2 matrices over the integers, that means you're looking at matrices whose entries are integers only. You might multiply 2 matrices. Look, I've multiplied 2 non-zero matrices and I got 0. This tells me that these two matrices are zero divisors, and in particular, 2 by 2 matrices is not a division ring. I can't say field because it's not commutative, but it's not a division ring. But even more than that, it has zero divisors, which means that it's not an integral domain in the sense of whatever integral domain means for non-commutative rings. We can't say integral domain because it's not commutative, but in any case, it's not it. It has zero divisors. And also note that even though I started by talking about matrices over the integers, you can think of this as matrices over the reals, or matrices over the complexes, or matrices having elements in F7. Any one of these these matrices could be from those and still give you zero, so still have zero divisors. In fact, you can even think of them as matrices over F3. If you think of matrices over F3, then that 4 in that first matrix becomes a 1. So this becomes 1, 2, 2, 1. And here I would get 1, and minus 2 is also 1. So I get 1, 1, and these would be 0, 0. But I still would get 0, 0, 0, 0, and I still would have zero divisors. So these are also have zero divisors. So these matrix rings behave very differently than, say, integral domains, which is what we're going to be studying in some detail in the lectures to follow. Okay. Now, for these matrix rings, let's just take a moment and talk about their groups of units. So if we start with a field and look at matrices, n by n matrices over the field, and say which ones are invertible, then that's a group that you're familiar with. The group of units of this this n by n matrices is just called the general linear group. And from group theory, you're familiar with that. The general linear group is exactly the set of invertible n by n matrices over a field F. However, if you have a general ring with identity, then the same situation works, but it's a slightly more complicated. We again also write GL and R, the general linear group over R, as the set of units, the set of invertible matrices. But what does that mean? So that means that GL and R is n by n invertible matrices, but with entries in R whose inverse is also in an n by n matrix over R. You might say, well, that's redundant, because if you say something is invertible, so you mean it has an inverse in that set. Yes, except for example, let's just look at one example. If you look at GLNZ, so this is the group of all invertible n by n integer matrices. But if I just say that, might be misleading, because you might think that all I just mean is that the integer matrices that have an inverse. But no, the inverse also has to have integer entries, whose inverse is also an integer matrix. So if you have an integer matrix whose inverse has a 1/2 or a 1/5, then that doesn't count, because then that doesn't live in the n by n matrices over the integers. So you only want those integer matrices that are invertible and their inverse is also an integer matrix. Which ones are those? Well, if you know your linear algebra, that's exactly how those integer matrices whose determinant is plus or minus 1. One way to see that is by the adjoint. There's a way of writing the inverse of a matrix using the adjoint, and that involves everything is integers except you have 1 over the determinant. And so if the determinant is plus or minus 1, you get integers. If it's not, you can easily not get in it. You have 1 over determinant in the denominator. Okay. Our next set of examples, in fact, our final set of examples on of rings, then we give a few examples of fields, is you start with a set and you look at functions. So I want to talk about rings that come from functions. And in some areas of analysis, these rings of functions play an important role. So S is all the functions from X to the real numbers, all the functions from X to the real number. And these are another way of thinking about it, the set of real valued maps on X. That's another way of saying the same thing. So how do I define addition and multiplication? I define them pointwise, and I'll say what I mean by that in a second. If you take two functions from X to the reals, then you add them and you get the function f plus g. But what is the function f plus g? F plus g is defined as f plus g on X is f of X plus g of X. And how do you define fg? Fg is again going to be a function. fg of x is f of x times g of x. And because the pointwise means that I'm defining one point at a time. If I know what f does to x and g does to x, I also know what f plus g does to x and fg does to x. And that's what pointwise means. And this is going to be a commutative ring with identity. The identity is going to be the function that sends everything to 1. That function, that constant function, is going to be the identity. The 0 is the function that sends everything to 0. Now you could also, this is, by the way, not an integral domain, as long as the set x, the domain of these functions, has at least 2 elements, because if it has at least 2 elements, you can take one of those elements and send it to 0 and send the other one to something else, and then switch. And then if you multiply those things, you will get 0. And then this will not be an integral domain. By the way, you can replace R, the reals, with other fields or even other commutative rings with identity. You do need some place where you can add and multiply, because the way we define addition and multiplication on functions involved adding f of x and g of x and multiplying f of x and g of x. So you can't have a function from one set to another set. It has to be someplace where you can add and multiply and so forth as well. Now, and I will give you another example of a ring of functions, but this will be a ring of endomorphisms. And first, I want to remind you, if you don't know, which most of you probably don't remember, what an endomorphism is. So you start with an abelian group written additively. An abelian group is you have closure, you have associativity, you have a 0, you have negatives, and it's abelian, meaning that it's commutative. So a plus b, and we write the elements as plus. So if you have a group homomorphism, so that means f of x plus y is f of x plus f of y, then that group homomorphism has another name. When it's a group of homomorphism from an abelian group to itself, it's called an endomorphism of A. And end A is the set of endomorphisms. So the elements of end A, each one of them is an endomorphism. So each one of them is a group homomorphism. So each one of them is a function. And this guy, we can define addition and multiplication on it as well. And the addition is defined just like the one we did before. F plus g at A is f of A plus g of A. Well, but we define multiplication differently. So define fg by function composition. Fg at A is f of g of A. And that makes sense because both f and g are maps from A to A. So if you compose them, you get another map from from A to A. And you can check and see that this is also a ring with identity, but not necessarily commutative, because function composition is not commutative. If you eat a chocolate bar, if you unwrap a chocolate bar and then eat it, that's very different than eating it and then trying to unwrap it. Functions are often not function composition. The way you combine two functions is often not commutative. Okay, now let's give some examples of fields. Fields are examples themselves are rings, but they're more than rings. They're when multiplication after throwing out 0 can never have an inverse, but after you throw out 0, everything you get a group and you have an identity and you have inverses. So some examples of infinite fields that you've seen: the set of rational numbers, the set of real numbers. These are all both with usual addition and multiplication of numbers, or the set of complex numbers. All of these are examples of infinite fields. If P is a prime, we have already talked about this. Fp, z mod pz with plus and multiplication, addition, multiplication, mod p is also a field. In fact, now this is a fact that I'm not ready to prove, but we will prove much later on in the chapters on Galois theory and field theory, that if p is a prime and n is a positive integer, then there's exactly one up to isomorphism finite field of order p to the n, a power of a prime. And those are the only finite fields. So in other words, there's no finite field of order 6. There's no finite field with 6 elements because 6 is not a power of a prime. But there's exactly one of order 9, and another one of order 27, and one of order 3. In fact, the one of order 3, you know what it is. It's z mod 3z with addition and multiplication, but you don't know what the other ones is. And even if you think you do, you don't. But again, this is a fact that there's only one of each one of those prime powers, and there's no other ones, and it needs a proof, will be proved much later in after we study field theory, which won't be for quite a while. Now, some other examples of fields. Notice that the integers are sitting inside the rational numbers. In fact, that's one of the things that we will, in a future lecture, explore. That when is an integral domain can be extended to a field, because the integer sitting in the rational numbers is actually very helpful, because we can do things in the rational numbers and then see how much of it carries over to the integers. One question might be the quadratic integer rings. Do they sit inside a nicely defined field? And the answer is yes. And so let D be an integer, positive or negative, not divisible by the square of a prime, the same usual condition. And define Q joint square root of D to be A plus B square root of D, where A and B are rational numbers. So this is in analogy with the way we define the quadratic integer rings, Z joint square root of D, where A and B were integers. Now A and B are rational numbers. So an element of something like this might be 1/2 plus 3/4 square root of D. Now, this guy is still an integral domain, but more than that, it's a field. Now, adding and multiplying two elements is not a problem. You can see that if you multiply and simplify, you will get another thing like this. But what about division? Can we actually divide? So does every element have an inverse? So let's start with an element, see if it has an inverse. If you have inverses, by the way, you can divide anything by anything, because alpha divided by beta is the same as alpha times 1 over beta. So if you have 1 over beta for all non-zero elements, then we can do that for everything. So 1 over A plus B square root of D, what can I do with that? Well, you can multiply top and bottom by the conjugate. And then what you get is, if you simplify it, you get A over A squared minus DB squared minus B over A squared minus DB squared square root of D. And as long as A and B are not zero, then we're good. And we have an element of Q joint square root of D. And so these are examples of what are called quadratic number fields. Okay, so I'm done with this lecture. This was the third in the series of lectures on rings, the examples of rings and fields. This was preceded by an original video where we talked about Diophantine equations and why we need to study rings to solve them. That was a motivational video. And then we had another video for rings, integral domains, and fields, where we defined and did some basic properties. And following this, we're going to have a very short video on subrings and the identity of a subring and the ring, comparing them. And then one on ring homomorphisms and kernels, and then ideals, which is sort of where all the action is. Till next time.